Thank you. Thank you. So I want to use my 20 minutes of fame to give some thoughts about the endeavors of interferometry, which is the science which I have been doing ever since I started my master's thesis in Moscow. So interferometry is, in fact, is a very simple thing. It's when you ask yourself a question, if I have 2 or 3 raindrops falling into water, what happens with these circles, with the waves which collide with each other? If you can answer these questions, you can master interferometry. In fact, if you can answer that question properly, you can use that information that is in these collision points between different raindrops to infer something about the falling stones in the water. So it is seemingly such useless or nonsensical questions that start the scientific endeavor. And the problem with scientific endeavor is that it usually takes such a long time that you cannot even predict which way it will take you once you start asking these questions. But I think it's probably the most human type of activity that we can enjoy on this planet. If you ask yourself the question, what's beyond my horizon? Just like this man here, this in engravings of Camille Flammarion, the Voyager, that just looks outside of his heavenly sphere and sees new horizons, new places. So, with interferometry, the Endeavour interferometry was also starting a very long time ago, about 350 years ago. And we're starting with some man named Isaac Newton, asking also usually quite nonsensical questions and uninteresting questions maybe. What happens with light if you put it through pieces of glass? And not only was asking this kind of questions, he was also doing damage to the royal properties in Cambridge, because anecdotal evidence says that he was, for his experiments, he was destroying the shutters of the windows or curtains of the windows of the royal palaces in Cambridge. So somebody allowed him to do that. And because he was allowed to do this, he made a very important conclusions. He thought that light is actually, when it bends and breaks into several colors in once it passes the prism, that light consists of particles. And there started a big debate, because after the invention of the telescopes, everybody was thinking that light was waves. And here comes Newton and says it's particles. And it's actually made a very big influence on the entire scientific debate for about 100 years, because Newton was such an authority, probably as big an authority as Einstein for us, that nobody was actually having guts to object to that and saying that it's not just particles, probably wave. And so it took about 150 years, almost 150 years, before people were starting amassing evidence that it is very difficult to understand many phenomena once you assume that photons or light is just particles. And this was the groundbreaking discovery, groundbreaking experiments made by Thomas Young. They're called double slit experiments. When you ask yourself the questions, what if you look into the room not just through one, but 2 keyholes at once? So in essence, you just light 2 small keyholes and ask yourself a question, what happens with light once it passes them through? And what he found out is that the light then forms a very peculiar patterns with light and dark stripes on the screen. And his conclusion was that the only way it is possible if light is actually waves. So that was one of the definitive arguments that light should have a wave-like nature. Well, since then we know that light is actually waves and also particles and many other things, waves and particles, probably everything, waves and particles, which only means that we don't really know what it is. It's probably something beyond that, but we need to keep asking this kind of questions, and then we should be able to answer, or give a better type of answers to some enigmas of the universe. So, luckily for Young, he was not alone. There were many other people investigating similar phenomena in optics, talking about what's going with the light when it passes through different types of lenses. And what they found out is that when the light passes through lenses, you get a response which is similar to what Young found in his experiments with the double slits. So these two patterns here, one of the stripes that comes from the Young's experiments with two slits, and another one stripes or circles which come out from diffraction response of a lens. And these patterns are all both proportional to the lambda, to the wavelengths of the light at which you use to produce them, and to the size of your experimental apparatus, which is the diameter of the lens, or the separation between the two slits. So from that, you can come to a conclusion that these things are actually similar and have a similar nature. And moreover, that you can actually, if you start producing these two slits in all kinds of configurations, so that you cover, say, 2 points on this lens, every 2 points will be just connected with each other through this kind of setup. You would be able to reconstruct the performance of a lens just from performances of many of these two slits arrangements. This was, or may have been, the thought, but it took another 150 years before you can actually turn these thoughts into real instruments. And it was happening in radio astronomy, because instead of these two slits or two holes in your lens, radio astronomers were using two telescopes put in different locations. And then you combine the signals from these two telescopes, and by combining the signals from more than two telescopes together and producing these pairwise combinations of those, you can actually reconstruct the telescope, which would be equal, the diameter of which will be equal to the largest separation between the telescopes you're actually having. So this is illustrated here, for instance. This is the locations of antenna of the American telescopes of Very Large Array. And you see this black line connecting the two antennas. So if you look at these two antennas as two holes of the Young's experiment, two slit experiments, this is the pattern. On the right-hand side, you see the pattern from that double slit that comes out from these two antennas. If you look at the other two antennas, different combinations, you see that pattern changes because it's proportional to the separations of the slits, and also depends on their orientation. So now, if you just combine all possible pairs of antennas in this 27 antenna telescope, and you combine these patterns which come from every pair of these antennas, you will get a pattern which is already resembling a point spread function, or the PSA, or the lens response you see on the right-hand side. And on the left-hand side, you see all these possible combinations, basically plotted, all possible pairwise combinations of different antennas. So they form just nice pattern here of 6-point stars. And the actual pairs of antennas which I showed before, you see them, they're marked here with the red circles. So now, this is good, almost good enough to combine it or to produce a big lens. But we want a lens which is actually totally filled. You see the dots here, they do not fill the entire circle. So what you can use to help yourself with reproducing or producing such a virtual lens is the Earth rotation. Because if you let this telescope sit there and look at this object for about 1 hour, each of these points will move because the telescope's orientation with respect to the sky will change. So you will get a situation like this. So within 1 hour, your pattern changes, and the resulting response of a lens, if you see on the right-hand side, slightly improves. If you sit for 3 hours, it gets even better. If you continue for about 12 hours, you see on the right-hand side, you almost a perfect response of a normal lens. So you reconstructed the telescope with an effective diameter of about 30 kilometers. So this is the essence of the interferometry. That's how the interferometric instruments work, not only in radio, but also in other domains. And now what I want to do for the rest of the talk is just basically give you the examples what we can do with our interferometric experiments and interferometric instruments, and mostly with the instrument called very long baseline interferometry, where you take these telescopes and they're separated not by 30 kilometers, not by 100 kilometers, but they are spread around the entire Earth. So the maximum separation will be about 12,000 kilometers. And you can add even the telescopes which would be in space. At the moment, we're working with a telescope which was as far away from the Earth is about 350,000 kilometers away from the Earth's surface. So what it gives us is that you know that in sensitivity of your instrument is proportional to the telescope diameter, or square root of that, the telescope area, and resolution is the wavelengths divided by telescope diameter. So with interferometry, if you add more telescopes, several telescopes together, then your sensitivity is determined by the sum of their areas. And the resolution is then given, as I said, by the largest separation between those telescopes. So you can really achieve very, very interesting results by doing this kind of applications. So the sensitivity of the radio astronomical telescopes have changed by a factor of more than 1 million ever since the first radio telescopes came about, since 1940, the first telescopes here. And then you see how the sensitivity improved with time. And all of the telescopes marked with the blue circles there are not a single dish instruments or a single telescope. Those are all interferometers, so combining many antennas together to work with that. So with the planned of future next generation radio interferometers such as SKA, we will be able to achieve such a good sensitivity to the radio signals that you will be able to see or to overhear the eavesdrops on the airport radar in a planet of about 50 light years away. So you could, if there is an airport there, you could actually see what they're doing there. You would be able to see something as minute as about an event that lasted of 1 nanoseconds. This is the computer capabilities of these new generations of telescopes. And you can measure the velocities of moving bodies to accuracy of about 1 centimeter per second. And there's another interesting aspect of the sensitivity of radio astronomical instruments. If you see this example below, you know that the cosmic rays, the most energetic cosmic rays, they travel. They have an energy of about 10 to 20 electron volts, and when they hit you, it's the same energy as the tennis ball at a speed of 100 kilometers an hour. Small cosmic rays. We're only lucky that they're so small they just go through. You don't get them to do much damage. But you compare it with radio astronomy, and all of the telescopes on Earth, working for 70 years, have collected energy which is smaller than the energy of one single falling snowflakes. So this is the difference between the energies, and that's the challenge of radio astronomy when you're talking about this kind of events. So all of the information that we collected from the universe and all of these wonderful discoveries, they carry with them the energy which is smaller than one falling snowflakes. So the other challenge in astronomy and in radio in particular was the achieving the better angular resolution. Why we need it, you've seen many times this year in the press releases dedicated to the imaging of the event horizon. And if we, this is one of the most fundamental questions in the present day astrophysics, what happens in the scales close to the event horizon. But if we want to solve these questions, you see that if you talk about the size of a black hole in a typical galaxy that we observe at about 1 billion years away, say, is 3 nano-arcseconds. And then when we count all these zeros here, if you want to convert it to a degree. Or 5 microarcseconds if we're talking about black hole in our own galaxy, and about 2.5 microarcseconds in the M87. So if you want to achieve this kind of resolutions, your interferometry is the only way available for us at the moment to do so. So if you look at that diagram on the right-hand side, you see the resolution of different instruments working in different domains of electromagnetic spectrum, from radio to gamma rays, and you see that radio instruments, they achieve a much better resolution than most of the existing telescopes. And this telescope called Maxim, it's one of the many incarnations of a proposed telescope to be working in X-rays and be actually also in interferometry. So with this kind of things, you need to, again, to go to interferometry in order to get the resolution which is sufficient to follow up such an interesting objects like black holes, cosmic black holes. And now, let me just go through some Hall of Fames of VLBI Hall of Fames. It's severely abridged because if you want to give a good account of the VLBI results, you probably need a few days, and that's what usually happens when people from VLBI observatories come together to discuss these new results. So, this is one that you cannot avoid this year. That's the Event Horizon image of M87. You've seen it about probably 55,000 times by now, in all kinds of reincarnation. But this is the new reincarnations. You see that image compared to the size of our solar system, confirming the results of the quiz. So essentially, but it's still, you can see how impressive it is. In a galaxy about 53 million light years away, you can resolve structures which are so much comparable to the solar system. You can see actually Pluto, if Pluto was there and the meeting was bright enough for you to be detected, to detect it. So the record resolution, angular resolution, is actually, at the moment, also belongs to radio astronomy, to the Space VLBI mission, Radio Astron, which, as I said before, combines telescopes on the ground with an antenna which can be separated as far as 350,000 kilometers away from the Earth. And that allows this kind of telescope to get an angular resolution of about 20 microarc seconds and reaching all the way down to about 10 microarc seconds. So if you think what is 10 microarc seconds, is 1 cent coin on the moon. And I forgot to mention on that diagram that, again, if you talk about these resolutions, that's what you see. 1 milliarc seconds is a man on the moon. 1 microarc seconds is a child on the sun. And I don't see if you see that in all of the screens, but 1 nanoarc seconds is what you were talking about. It's the football field on Alpha Centauri. So you need to be with 3 nanoarc seconds to detect these black holes or image black holes in the distant galaxies. 1 nanoarc seconds, with 1 nanoarc seconds, you would see football fields on Alpha Centauri. Not quite the score of the game, but still approaching these kind of capabilities. So we do now 10 microarc seconds. It's way away from 1 nanoarc seconds. We probably can reach it, but not anytime soon. But what we can see now is that at this kind of resolution, everything is live. Nothing really is still in the sky. If you look at any source for about 200 days, and you see how much evolution happens there, how much changes there. It's really alive pictures, and not only on the Earth. You can actually, by virtue of providing such a beautiful angular resolution accuracy on the sky, you actually get the same accuracy, or extremely good accuracy, on the positions of the radio telescopes on the Earth. And by doing that, you can actually measure the continental drift. There's all these measurements, not all of them come from VLBI, but a majority and most accurate measurements come from measuring VLBI, observing VLBI distant quasars. So you not only know things about the quasar, you also know things about the continental drifts on the ground. Another thing, if with astrometric applications of VLBI, you establish the most accurate inertial reference frame, which is extremely important for the space navigations, for the military applications, and for civil applications, such as your typical navigator or your iPhone. Your iPhone uses GPS in order to provide you with the information about the next store, cafe, whatever. But if the GPS was not corrected with the help of the measurements done with radio interferometry, you will be terribly off within a couple of weeks, because the GPS needs to be corrected continuously in order to provide this information, sufficient accuracy on Earth. So VLBI helps that, and this is one of these tasks that you really do not usually being aware of the usage of such a usage of radio interferometry. Now, as I said, everything is changing with such a resolution, and you can even see the nonlinear effects of the solar motion through the galaxy, which is in a way is an amazing thing. Is that you realize that the sun takes about 225 million years to turn around the galaxy, and we already see this. We can actually see this. You see the vectors here. This is the systematic offsets in positions of the distant quasars measured with VLBI, and you see they form a particular pattern, which basically, which reflects this curvilinear motion of the sun around the galaxy. So we know that, or you can actually sense it in a way with this kind of measurements, the motion of the sun around the galaxy. And finally, as I said, the next generation of interferometers will provide extremely good sensitivity, but not only that, it will also provide extremely good angular resolution. The mission, which is now planned, is going to be put at about 1.5 million kilometers away from the Earth. So the yellow dot here is the sun, the blue one is the moon, is the Earth, and then there's 1.5 billion kilometers away from it is the point where the this telescope millimetron will be placed. So at these separations, it would really approaching the 1 nanorec mark. So with this telescope, would be really able to see or start looking at football fields on Alpha Centauri. Of course, they're not bright enough for us, but what it would be bright enough is the potential investigations of such enigmatic objects as wormholes, which in some theoretical minds connect different parts of the universe together by basically piercing the habitual topology of the three-dimensional space. And in order to observe this kind of wormholes, you really need to get to this 1 nanorec resolution benchmark. So that's how VLBI will continue help us to get the new answers to these and these greatest questions of physics and astrophysics. So let me just finish again. This was a long journey for interferometry, starting from 1666. So with this kind of damaging experiments done by Isaac Newton. But you can ask yourself a question, just to think about it. What if they did not allow him to do that? What would have happened with us? What would know about the spectrum of light? What would know about the dispersion? What would know about the other things? And that's a question which we should ask every time we think that the fundamental science does something nonsensical. It may be doing something nonsensical from our point of view. It was totally nonsensical from the point of view of people from the 17th century. But 4 centuries later, you can do wonders with the things that started so long ago. Thank you.